All right, welcome back. Here we are, chapter 12, section 2. We'll do this. We'll work it up kind of along as the first one. So we're talking about inference for two-way tables. Sometimes this can be a little cumbersome, but we'll work through it. And here we go. Again, we have these different learning goals. Sorry. So we're going to test for homogeneity, easy to say, stating hypotheses is what we're going to be talking about first of all. So does background music influence what customers buy? One experiment in a European restaurant compared three randomly assigned treatments. There's no music, French accordion, and Italian string music. Now, under each condition, the researchers recorded the number of customers who ordered French, Italian, and other entrees. All right, so our null hypothesis is that there is no difference in the true distributions of entrees ordered. And of course, our alternative is that there is a difference that we have. Okay, so now remember, the alternative hypothesis does not state that each distribution is different from each of the others. Okay, so that's, be careful what we're saying here. All right, so here's our two-way table. Type of background music, entree ordered, there we go, with the totals of the rows and columns and the overall total of 243. So, all right, so let's take a look and see what happens. So again, we can kind of look at the percent that ordered each French, Italian, and other entree with no music, French, and Italian. And the differences in these distributions might provide convincing evidence that background music affects it. Or is it plausible that the background music has no effect? And again, and these differences are due to the chance involved in random assignment of treatments. Who knows? That's kind of what we're going to try to figure out here. Now, we could compare many pairs of proportions, ending up with many tests and many p-values. And again, that's a bad idea. And the reason for that is that the more of those tests that we have, the bigger probability that we're going to make a type 1 error on one or more of those tests. So the problem of how to do many comparisons at once without increasing the probability of a type 1 error is common in statistics. Now, statistical methods for dealing with multiple comparisons usually have two steps. One, perform an overall test to see if there's convincing evidence of any differences among the parameters that we may want to compare. And then when the overall test shows that there is convincing evidence, perform a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences really are. Okay, so here we are. Here it is. Again, we're going to try to find the expected counts. We're going to start by assuming, let's assume that the null hypothesis is true, is that we have that makes a difference. Okay, so is the specific type of music that's playing has no effect on entree orders? The proportion of French entrees orders under each music condition should be, well, according to French, we have 99 out of 243, which is 0.4074. So that should be that proportion. Now, because there were 84 total entrees ordered when no music was playing, we would expect, well, if we did that 84 times that proportion of 0.4074, and if we equal that, we should have 34. Yeah, that was a typo there. 841, say 884 times 0.4074 should be 34.22. Now, again, what we did see was 30. Okay, so there is a difference there. Now, again, that's kind of what we're going to figure out is what should be and what's observed. Okay, so what we're going to do is calculating the expected counts for a chi-square test based on data in a two-way table. What we're going to do is we're going to assume that null hypothesis is true. So the way to do that is to take that row total, to get that expected count that goes in that column. We're going to take that row total that we have, the 99. We're going to multiply it by the column total of 84, and then we're going to divide it by the table total, 243. So that's how you're going to find those. You're going to go through each one of those and find what that expected count is. All right, now with chi-square tests for goodness of fit, the expected count should not be rounded. While the observed count of entrees ordered must be a whole number. An expected number is not. It's like when you take the average. You can get half or get some fraction that are decimal that's not necessarily true. So keep that in mind. Don't round those. Don't round those. Okay, so chi-squared, remember, is our observed count minus the expected count squared divided by the expected count, and we have that taken care of. So the sum is over all cells, not including the totals, in the two-way table. So again, we're going to do that for each one. All right, we're going to get our chi-squared of 18.28. Again, we can use the calculator, and again, when we're doing this, it might be good just to kind of show not all of them, but show what you're doing, and then go to the calculator for that. All right, and again, we kind of talked about that right there. All right, so here we go. So for class project, Abby and Mia wanted to know if the gender of an interviewer could affect the response to a survey question. The subjects in their experiment were 100 males from their school. Half the males were randomly assigned to be asked, would you vote for a female president, by a female interview. The other half, same question by a male interview, and the table shows the results. So we're going to state the appropriate null and alternative hypothesis. We're going to show the calculations for that expected count. And then we're going to calculate the chi-square test statistic. Okay, a lot of things to do there. Okay, so here we go. So the null hypothesis is that there is no difference in whether they're asked by a male or female, and the alternative is that, yeah, we think there is a difference. Okay, so the expected count. So once again, we're not going to show this for every single one, but we take the 69 right here times the 50 divided by the 100. That's how you get that number right here. It's the 34.5. That's what you're doing right there. All right, and then so we kind of did that for each one that we had. Okay, so again, each one of those you'll see fits in that same category there. So, all right, so we have those numbers filled in. We're all set. Okay, so our chi-squared, we'd have to go through and do those again. Look at the way to do this for the on the tech corner. It's kind of a good way if you can put some things into a matrix and you can actually figure it out. It's actually pretty cool on how to do that. They know how to do that, figure that out from that matrix. So take a look at that tech video, and we'll run through some in class too. So again, here we go. So we're going to check those conditions here as we go. Yeah, so there it is. We calculated that the chi-squared was 4.25. We're going to verify the conditions are met. Okay, so we're going to do that. We're going to use, well, I like the calculator. We'll use the calculator to find the chi-squared p-value, and we're going to interpret that and draw some conclusions here. So here it is. Put it all together here. Here it is. Let's verify the conditions are met. It is random. The counts are greater than 5. That's the table. You can see that on the table of expected counts. And again, they didn't check the 10% condition because they go from the same population, so we're okay there. All right, so going to our calculator again, I would go ahead and put that in the calculator to find our chi-squared and our p-value. Again, we do find it more accurately. It's 0.119. If you do the table, it's between 0.10 and 0.15. So I like the 0.119. Well, that's our p-value. Okay, so what we're saying is that assuming that the gender of the interview doesn't affect responses to the question, there is a 0.119 probability of observing differences in distributions of responses larger than those in the study by chance alone. That's the probability of that happening. So what conclusion can we draw? Well, because that p-value is bigger than 0.05, we are going to fail to reject it. We're going to say there is not convincing evidence of a difference in the true distributions of response to this question when asked by male or female. Okay, so a lot of work there to go through that. But yeah, good work nonetheless. Now again, use the technology. Again, check out when we do this. It's number 13 or 30. Is it 30? 30. Yeah, Tech Video 30 does a really nice job of showing how to put this in a matrix, get all the calculations done. They do a really nice job of, that's the observed, that's matrix A when you do the chi-square test, and you can put that in, and it'll do the expected values for you, actually figure those out for you, and then you're able to get your chi-square value and your probability of 0.0010. It's really kind of a slick way of doing it. So again, I would suggest doing that. And again, it will actually tell you what matrix B is too. If you go back, it actually fills it in for you. So it's really kind of a good deal. So once again, using the calculator, make sure you're showing the first few calculations and then go from there. All right, so let's put it all together. All right, so we're going to do a chi-square test for homogeneity. Okay, oh, can't even say it. So we're going to do that. So here it is. We're back to this. The Pew Research Center conducts surveys about a variety of topics in many different countries. In one survey, it wanted to investigate how residents in different countries feel about the importance of speaking the national language. So we have all of that in that two-way table. Okay, so once again, what we're going to do is we're going to see if it convinces, if we have convincing evidence that it does. We're going to do the null hypothesis that there is no difference. The alternative is that there is, and that we're going to use a 5% significance level. They are random. The 10% condition does hold true, and that all of the expected counts, if you look at the table that we do below, they are over 5 as we do those. So again, we have those expected counts there. Again, we can use that calculator to do those as well. So look at that Tech Corner video. All right, the do. So we go ahead and we figure out, and again, I'd use the technology of finding that, you know, the p-value actually is extremely small. In fact, it's such a small number. It's actually zero. Really, is what it is what we figure out. So we're going to conclude that basically because the p-value is so small, it's really close to, it's really zero. We're going to reject the null hypothesis, and we are going to say that there is a difference in the true distributions of opinions about English, speaking English for residents of Australia, the UK, and the US. Okay, just a couple tips here as we talk about this. Many students lose credit because they don't write down and label the expected counts in their response. Okay, so you got to make sure you show that, and again, use that calculator to compute that. It goes really quick. And then, of course, like I said, we'll pick this up tomorrow is what we'll figure out. So 56, yeah, this is where we're going to stop for today, and we'll pick the rest up. And until next time, I'm Mr. Boone.